we arrive again at the solid, but now to consider not the atomic structure, I mean, not the way in which the atoms are bonded to form the solid, but how they are located, how they are arranged to form the crystal. Of course, the first concept we must clear up is the concept of order. It's clear that's an order series of items, of objects, and here is disorder. When we go to a crystal, we can have basically two kinds or two ranges of order: long range order and short range order. In the case, for instance, this is a window glass, it's amorphous material. That means there is no long range order. However, if we go at the short range, it's perfectly ordered. I mean, all the atoms are located in the way they must be located. Here are the angles and the tetrahedral structure, everything is ordered. The only is that if I move a little bit far away from the point and consider this order is not preserved. I mean, there is no way to repeat. There is no unit that can be repeated. In the case of the long range order, then we have the crystals in the sense of crystal structure, and then we don't have not only order at a short range, so at the level of the molecules, but also we can find put the cursor, but we can find here a unit that can be repeated to cover all the crystal. We can repeat this unit in an infinite way, then we can construct a crystal. So we have crystalline materials. In crystalline materials, we have both short and long range order. Ideally, these are single crystals. That's not only we have long range order, but this long range order is the same all over the crystal. Yeah? Or we can have polycrystalline materials. In this case, it's true that we have still long range order, but we can have different regions with the order is slightly different. For instance, we can have some misorientation in the planes, the crystal planes, or some dislocation, some boundaries. Still, there are long range order, but we can distinguish different areas in which the order is slightly different from one to another. And then we have liquid crystals. In liquid crystal, we have short range order, and also we have some long range order, but only over small regions. The difference with polycrystalline materials is that in the case of polycrystalline materials, it's true that we can distinguish different regions with orders slightly different, but still highly ordered, yeah, and still big regions in micro scale. In the case of liquid crystals, the regions over which the order is preserved are really small, and also this long range order is not as perfect as it is in the case of polycrystalline materials, in the case of single crystals. And of course, we have amorphous materials in which no long range order at all is present. Okay. Well, let's come to the concept of order. And we have some concepts that are very important when we are going to describe the crystals. First is the lattice. Lattice is an ordered series of points that divide the plane or the space in a regular way. The base is the atom or group of atoms associated to each lattice point. If we join these two concepts, these two ideas, lattice and base, then we have a crystal. So the crystal is the set of lattice plus base. Unit cell is this minimum portion of this unit I told you before, that retains all the characteristics of the crystal and allows the reconstruction, the full reconstruction of the crystals by means of a series of symmetry operations. Then, so here we have the lattice, here we have the base, that's the crystal lattice plus base. And then we can have the unit cell, that is this minimum region that let us to reconstruct, to reproduce the full crystal. Besides these concepts, then we can also have atomic radius, which is also quite important to determine and to define the crystal structure. We are going to understand, or we are going to define this atomic radius as the apparent radius of the atoms, calculated as if the atoms were rigid spheres occupying as much space as possible along a compact direction. This is going to be our atomic radius. Yeah? It's not the normal concept, that is the idea that is going to be more useful for working with crystal and crystal lattices. And then we have the packing factor, which is the fraction of the cell volume occupied by atoms. Okay, we have depicted an image which is quite simple, one-dimensional crystals, but of course crystals are not one-dimensional, but three-dimensional. And we know that some symmetry conditions must be preserved if we want to have a unit that allows us to reproduce the whole crystal or infinite regions. Okay, we combine all these elements, then we find that only seven crystal systems are possible, which are depicted here. There is a I'll tell you afterwards some applications, some app which you can play a little bit around these concepts. So these crystal systems are cubic, tetragonal, orthorhombic, hexagonal, rhombohedral or trigonal, both are valid names, monoclinic and triclinic. Symmetry is decreasing when we go down in this table. So for the cubic crystal, all the axes are equal and all the angles are not only equal but 90 degrees. In the case of the tetragonal, then we have an axis which is different, which is C. Still, the three angles are the same, 90 degrees. In the orthorhombic, angles are preserved, but three axes are different. Hexagonal, A equals B, but not C, and two angles are 90, and gamma, the third angle, is 120. And then for the rhombohedral or trigonal, and the symmetry is decreasing, as you know here. And then in the case of the triclinic, which is the crystal system with the lowest possible symmetry, then we have all the three axes are different and all the three angles are different and different from 90 degrees. Here you have the notation. This is the normal way to name the axes A, B, and C in a trigonal system. In the normal, this could be X, Y, and Z. The volume of the cells, which is quite simple in the case of the cubic, tetragonal, or orthorhombic, and not so simple when we go to the hexagonal, and it's more and more complicated as we go to systems in which the parameters are more different from one direction to the other direction. In the case of the cubic, we have three possibilities to create or to build up a cubic crystal. The simplest one is the primitive cell, so we have only one atom per cell. Atoms are placed at the vortex, and they are served with the other cells, and it's only one atom per cell because we must take into account, we'll come later to this point, we must take into account that this atom is shared with the other cells adjacent to it. So one there, two, so here 4, and here down 4, so 8, then 8 divided by 8 is 1. So we have one atom per cell, but we have also the possibility to have which is called non-primitive cells. Non-primitive cells are cells that are unit cells, so they will allow also to reproduce the full crystal, just applying symmetry operations, but they are not primitive in the sense that they have more than one atom per unit cell. In this case, body-centered cubic, we have two atoms. For the atom at the corner, it applies the same as in the simple cubic. So one atom shared by 8 cells, then 1/8 of atom multiplied by these 8 corners, so one atom. But now we have an additional atom at the center of the cube. So that means that this atom, which is at the center of the cube, is not shared by any other cell because it's inside the cell. So it's count full. So we'll have one atom, two atoms. And the other possibility for a non-primitive cell in the case of a cubic system is the face-centered cubic. In this case, the additional atoms are not at the center of the cube, but at the center of the faces. So that means that each atom at the center of a face is shared by two faces. So we have three possible cubic systems: simple, face-centered, body-centered. Only simple is primitive. Then we have two possible tetragonal systems. Again, simple, which is primitive, or body-centered, which is not primitive. Hexagonal. Then we have for the orthorhombic, we have four possibilities: simple, body-centered, base-centered, or face-centered. This is the same as in the case of cubic, but additionally, we have the possibility to have an atom at the base of the unit cell. So this is the base center. Then we have monoclinic. Again, two possibilities: simple and base-centered, trigonal, and triclinic. In total, we have only 14 possibilities, which are known as the 14 Bravais lattices. So we have lattice, base, crystal, unit cell, and then we can go from 1D, 2D, or 3D. But we had mentioned two other concepts, were atomic radius and packing factor. So now we come to these factors again to see the importance of these two parameters, these two concepts in the construction of the crystal. First, we must learn how to count atoms in the cell. I already told you. For instance, here is the cubic, simple cubic, 8 edges, one atom at each edge. Sorry for the dyslexic. And then here is, you have one cell, 2, 3, 4, 5, 6, 7, 8 cells. So this atom, for instance, here is shared by the 8 cells. Here again, the same if I put the additional cells here, so I consider that one. Then it's shared by 8, so each corner is shared by 8 cells. Therefore, we only count 1/8 for each corner. 8 corners, one atom per cell. PCC, as told, we have here the possibility of an additional atom, 8 times 1/8 plus 1, 2. And in the case of FCC, face-centered cubic, then we have each corner again is shared by 8 cells, but now each of the 6 faces is shared by 2 faces, by 2 cells. So 6 times 1/2, then in total it makes 4 atoms. So simple cubic unit cell has 1 atom, body-centered cubic has 2 atoms, face-centered cubic has 4 atoms. And now an exercise: determine the number of lattice points in the unit cell of the other crystal systems. That's for you. Okay, due to some, we always are looking for, we look for the equilibrium position, the equilibrium configuration, and the crystal is going to be the equilibrium configuration. we need a balance in energy. To get it balanced, atoms will tend to be placed in the cell as compactly as possible, because it will maximize the binding energies, and then minimize the crystal energy. It also has a counterpart, so to say. I mean, the atoms can be as close as we want, but we reach a point in which they cannot compact any longer, because they are somehow touching on each other. Okay, then we can see in the complementary way. Okay, the size of the cell will be that necessary to accommodate the atoms, because the atoms cannot interpenetrate. Then it comes our concept or atomic radius. It's the apparent radius of the atoms, calculated as if the atoms were rigid spheres, not interpenetrating, occupying as much space as possible along the most compact direction. Along the most compact direction, because we are looking for the maximum cell. So, cubic simple, or simple cubic. Simple cubic, the most compact direction is the edge. We have maximum, we can have two atoms, and maximum, if they must touch each other, then it's the 2 times 2r. Then we have r, 2r, then 2r equals a sub 0, the edge. In the case of the BCC, then the most compact direction is that joining two atoms in the corners and the central atom, cube diagonal. In the case of face-centered cubic, of course, is a diagonal, but not the cube diagonal, but the face diagonal. That's the difference. Here is this part, or this, or this. However, in the cubic center, you have it here. Is from here, from this corner to this opposite corner. Okay. With the hints, estimate the relationship between the lattice parameter and atomic radius in all cubic structures. Yeah. Then we come to the packing factor, and we are going to we are going to calculate the fraction of the cell volume which is occupied by atoms. Always the simplest is the cubic. In a cell, well, let's go to the face-centered cubic. So in a cell, there can be up to 4 atoms. Spherical, radius r, so they will occupy volume 4 times 4 over 3 pi r to 3. This is the sphere volume. Yeah. On the other hand, the volume of the cubic cell will be, it's cubic. The parameter is a0, so a0 to 3 to cube. That's the volume cell. And then the packing factor, it must be the ratio between these two volumes, V sub A, V sub C. If it's the volume occupied by the atoms divided by the volume of the cell. And then the packing factor is this number. This is the ideal packing factor. Yeah, it's the ideal packing factor for the FCC. Now we can determine the density, for instance, of iron. Iron can have two different crystal structures, either BCC or FCC. Let's go for the BCC. In the case of the BCC, the lattice parameters are 0.2866 nanometers. This is the atomic weight of iron density. Of course, we will need to know the mass and volume of the cell. For the unit cell mass, we have the number of atoms in the cell multiplied by the atomic weight of each atom, and of course divided by the Avogadro's number, because here we have this is the atom gamma small, and the volume of the unit cell, as told, is 0 to the cubic power. Make all the values, and this is the value we obtain for the density, 7.8, 7.9 grams per cubic centimeter. Let's come to some other concepts which are also very important when we are trying to describe the crystals. First is we are going to, just for the sake of simplicity, everything is valid in any other kind of crystal or crystal system, but the description is much more complicated. So just for the sake of simplicity, we'll focus on the cubic system. Now we know what the primitive cell is and the volume, what the unit cell is and its volume. We know how to count the number of atoms per unit cell, and we know also how to calculate the packing factor. Still, there are some things we still do not know, as the position of the lattice point relative to the cell origin, whatever the cell origin is. We must define what the number of first neighbors is. Also, we must define the distance between these first neighbors. Also important for some applications and for some properties is the number of second neighbors. Of course, the interaction between first neighbors is much larger than between second neighbors, but in many cases it's also important. And of course, the distance between these second neighbors. So let's come to define. First, simple cubic, the simplest. I have depicted here just these four cells for simplicity. I define three factors: L, X, M, Y, and zeta, and this is the way to define the vector that will define the cell edge. Okay, we have one lattice point, let's say at 0, 0, 0. The origin is completely arbitrary, but it's not necessary to complicate it more. Unit cell, primitive cell volume. In this case, both are the same. As for first neighbors, we have 6 first neighbors here. This is our reference atom. So 1, 2, 3, 4, 5, 6, which are located at these points indicated here: plus, minus 1, 0, 0, 0, plus, minus 1, 0, and this. And the distance, of course, between these neighbors is A, the edge. As the number of second neighbors are going to be the diagonals, so are 12 located at these positions, and the distance between the second neighbors is told as the diagonal, the face diagonal, because this is the first neighbor, the next atom, the nearest atom after this one is the one here. So the diagonal, the distance between second neighbors is then a square root of 2, and the packing factor is 0.5. Remember that the packing factor we have calculated for the face center cubic, it was 0.74. So in fact, the face center cubic is much more compact than the simple cubic. So here you have all the second neighbors and the first neighbors. In the case of the center cubic, we have 2 lattice points. Again, this is my reference cell. Origin 0, 0, 0, or 1. It's the one you want, but I have written 0, 0, 0. Then the second atom in the cell is 1/2, 1/2, 1/2, just at the center of the cube. Unit cell volume 8 to 3, primitive cell volume 8 to 3 divided by 2. Number of first neighbors 8, located at plus minus 1/2, 1/2, 1/2, are marked here. The distance, half the diagonal of the cube. Number of second neighbors, 6. Plus minus 1, 0, 0, and successively, and the distance between second neighbors, which is a, and again, the packing factor is slightly higher than in the case of the simple cubic, but still does not reach the value for the face-centered cubic. In the case of the face-centered cubic, the discussion is a little bit more complicated because we have more atoms, of course. Here you have the reference one, 0, 0, 0. Then you have the other atoms in the cell, and these are first the lattice points, the number of first neighbors that are either this pink or green, of course, located at these positions. Distance, diagonal, but not for the cube, but for the face, and the number of second neighbors, which is either this green or blue, depending on how they are, which are placed, the distance is a, so the full edge, and now we have the packing factor we have mentioned before, 0.74. This is from the cubic structure, is the most compactly packed, the most closely packed. So let us summarize. For the cubic, this is the differences you have calculated it before in the exercise. The ratio lattice parameter versus atomic radius, atoms per unit cell, coordination number 6, 8, 12, 12. You see in the face-centered cubic, in the packed hexagonal cubic crystal, the coordination number is too high. If you remember, when we were talking about the metallic bond, one of the things we have to explain is that the metals are very compact structures, and many elements are metals because, as I have told, the general trend is to be as compact as possible to minimize the energy. So that means to go for the most compact structures we can have, which are the cubic and the hexagonal, both with the same packing factor. And here we have examples of several materials, and here I have polonium, alpha manganese, cesium chloride, iron, titanium, wolframium, molybdenum. And I have, for instance, here written iron because iron maybe in a body-centered cubic or a face-centered cubic, titanium, maybe either face-centered cubic or hexagonal, and so on. Okay. As usually, an important crystal is also the hexagonal. In the case of hexagonal, we have 12 atoms at the corners that are served by 6 cells, and 2 atoms of the bases, which are shared by 2 cells. So 3 atoms in total. But this is not the cell, and that's very important because it's a trick, and it's quite tricky, and it's an important source of silly mistakes. This is the cell. This is the unit cell, not this one. If you see here, the unit cell, this unit cell is the same as this unit cell here, so this part. That means that when we represent the crystal, the hexagonal crystal, then in fact we are representing 3 unit cells altogether. 1, 2, half, half. So 1, 2, 3. Yeah. In the case of the packed hexagonal, it's a variety in which additionally we can have 3 inner atoms, which are placed in these positions. Again, taking into account that this is not the unit cell, and the unit cell is the same as here, this square prism, and an atom inside. And in this case, we have 2 atoms per cell. So 1 atom per cell or 2 atoms per cell in the packet hexagonal. Be careful, because this is quite frequently it's the mistake is made. Yeah. Then come to the way to pack these spheres. Now we are packing spheres as closely as we can. So this we make this layer of spheres. These are atoms. Now we must place a second. We have here two different possibilities. We have this kind of holes, this kind of positions, or this kind of positions. If we use these kind of positions, yeah, it's red over red, and it's not so clearly seen, but I am also here with the arrow. Then this is our layer B. Yeah. Now, here I have hole, here I have hole, here I have a hole. So I have two different kind of positions where I can place the third layer. I can go for this configuration, so A position, B position, C position. This is the same as this one, and this is occupying this hole here. Or we can go for A, B, but then A. See the difference between the position of this C atom or this A atom. Yeah, you see the piling, the stacking is different. So this is the difference between the cubic center, face center cubic, or the hexagonal packing. This is hexagonal packing, and this is the cubic packing. And it's important, yeah, because many properties are going to be defined by this difference. In fact, you see that here the difference is clear in terms of the unit cell when we will be in plane. So here we have another way to view. This is stacking sequence. This is a stacking sequence for the hexagonal. So A, B, A. You see here the positions. And if we go for the cubic, A, B, C, and then we come back to A. So you have this. This is, for instance, this could be equivalent to this. It is there. This one is the same, but then we have the other one, which is the complementary. So we have here a stacking fold. The stacking sequence is A, B, A for the cubic, for the face center cubic, A, B, C, A, B, C. Nevertheless, there are these two structures are quite similar, and so it's possible, and one of the important things that occur with quite a lot of frequency in many metals is that they are in the same crystal. We can find both structures. Also, is the origin of part of the allotropes or polymorphism that occurs in many materials. So we come to this concept of allotropy and polymorphism, and we talk about allotropy and polymorphism when the same element or the same compound can be present in different crystalline structures, depending on the pressure, temperature conditions, growing conditions, a lot of parameters. So, classical example, iron. Here is iron alpha phase, which is body center cubic. Here is iron gamma phase, which is phase center cubic. This is called ferrite. This is called austenite. This is the phase that more stable at high temperature. This is the phase more stable at low temperature. In most extreme case, we have already talked about that, is diamond and graphite. This is diamond, and this is graphite. So it's two allotropes. The terms allotropy and polymorphism are practically the same. However, when we refer to elements, normally we use allotropy, and when we refer to compounds, it's more common to use the term polymorphism. Okay? So we are going to calculate the change in the volume into polymers. For instance, zirconium oxide. Zirconium oxide can have two different crystal structures. It can be either tetragonal or monoclinic. These are the lattice parameters for the monoclinic phase. and for the lattice parameters for the tetragonal phase. As you may remember, or come back to the last slide, in the monoclinic phase, the three axes were different, and the angles two angles were equal, and there was different. And in the case of the tetragonal phase, two axes were identical, the third axis was different, and the three angles were 90 degrees. So it's not indicated here. These are the volumes for the tetragonal cell and for the monoclinic cell. We made the calculations in cubic armstrongs, percentage of volume change, and then you see that we have an expansion of around 1.5%. It's not bad. I can tell you, for instance, that if you try to grow zirconium oxide in the furnace to grow samples, it explodes. So this different expansion coefficient, it's enough, and the material explodes, and you get just a mesh of small crystals, but you don't get them. If you place in the furnace a pellet of zirconium oxide and you heat up, it will explode. Also because it's ceramic, which is very fragile, so greater than 0.1 are not affordable. So it's besides the academic interest that can have this kind of exercises, that can be also interesting for many applications. So now we are going to design an element which is capable to detect volume changes of 1 cubic centimeter with an accuracy below 1%. Yeah? These are the data for the iron in BCC and FCC phases. Here we have passed the transition temperature. This is for the BCC, the volume, and for the FCC. Of course, the atoms do not disappear, so we must compare units with the same number of atoms. That is, 1 FCC is equivalent to 2 BCC in terms of volume. So this is the variation of volume. So a new cube will have a volume of a little bit less than 1 cubic centimeter expected. If we want an accuracy of 1%, the sensor must detect changes in volume which are about 0.000134 cubic centimeters. Yeah. I strongly recommend you to go to this page, DoItPOMS, because then you can play. You have a lot of flash animations, and so you can play with a lot of things, a lot of concepts related to lattices, unit cell, the geometry, the cell structure, the packing efficiency, etc. Okay. Then we need to look for notation, because now, okay, we have described the crystal, but if I must tell someone else how my crystal is, it's very difficult, because I have not developed a real notation, clear notation to do that. So I should have, okay, it's like a cube, and so the atoms are placed in the diagonals of the cube, or it's complicated. Then in the next lesson, we are going to develop this notation to refer to the crystals.